Hello, this is Terry Collins. Welcome back. The title of this lesson is Adverse Effects of Chemicals on Health and the Environment. In this lesson, we'll review the history of the beginning of the oil and chemical industries. We'll highlight a false premise that has historically underpinned the chemical enterprise. And we'll introduce the range of adverse effects of chemicals on health and the environment that green chemists must design against. The oil industry is a central building block of our modern high-technology civilization, and it provides the principal feedstocks for the chemical industry. Where and when did it start? Well, it turns out that this gentleman, Edwin Drake, discovered oil on August 27, 28, 1859 in Titusville, Pennsylvania, at what became the first commercial oil well. Titusville is about 100 miles north of Pittsburgh, Pennsylvania. Here is a picture of Edwin Drake's first oil well in Titusville. Drake's oil well incorporated important innovations and was widely copied, leading to an oil boom in western Pennsylvania that rivaled the California gold rush of 1849. One of the really important points to note is that the modern oil industry is only about 150 years old. The chemical industry is also a critical part of our modern civilization. Where and when did it start? This is a picture of William Henry Perkin towards the end of his life. At 15 years of age, Perkin entered the Royal College of Chemistry in London and began studies under August Wilhelm von Hofmann, working to synthesize quinine, an expensive natural substance much in demand for the treatment of malaria. During the Easter vacation of 1856, when he was only 17, and while Hofmann was visiting his native Germany, Perkin performed some experiments in a crude laboratory at his home in Cable Street in East London, and he found that aniline could be partly transformed into a crude mixture, which when extracted with alcohol produced a substance with an intense purple color. After further development with his brother Thomas and a friend Arthur Church in a hut in the Perkins' backyard, Perkin filed for a patent in 1856, and this substance became the first commercial dye, which they named Movane, giving birth to the synthetic dyeing industry and beginning the modern era of the corporate chemical enterprise. The structure of Movane has only been known accurately since 1994. It's actually a complex mixture of purple dyes. The Perkin home today is marked with this blue plaque. Well, since that time, chemists have prepared an enormous number and variety of new chemicals. In fact, 87,000 chemicals are listed in the EPA Toxic Substances Control Act inventory, which means that they are permitted to be in commerce in the United States. Not all of these chemicals are actively in commerce. In fact, according to Michael Walls of the American Chemistry Council, only about 10% of the inventory, about 8,300 chemicals, is in actual commerce in significant amounts. One of the key points here again is that the modern chemical industry is only about 150 years old. In subsequent lessons on sustainability ethics, we will learn from Hans Jonas that a new ethics is needed to enable us to better deal with the immense power that the oil, chemical, and related industries have given us over the ecosphere in just this very short period of human history. Another important point is that there is an underlying premise on which the chemical enterprise has been built. Never stated explicitly, but there for almost the entire 150-year period of building of the chemical enterprise. A premise which assumes that any useful chemical, commercialized for purposes that are not related to health or the environment, will not have a profound impact on health and the environment. In other words, the chemical will give its high technical performance and its high cost benefits, the reasons of course that it's being commercialized, and it will be well behaved, with adverse effects on the health and the environment being non-existent or at least negligible. This premise is profoundly wrong. A large number of chemicals exhibit adverse effects on health and the environment. Let us now consider what an adverse effect is considered to be. An adverse effect has been defined as change in the morphology, physiology, growth, development, reproduction or lifespan of an organism, system, or population or subpopulation that results in an impairment of functional capacity, an impairment of the capacity to compensate for additional stress, or an increase in susceptibility to other influences. The California Department of Toxic Substances Control has recently released a draft regulation for safer consumer products. The aim of the department is to stimulate the replacement of hazardous substances in the commercial products and processes of California, while assuring that alternatives are also as safe as they can possibly be. So in treating adverse public health impacts, the department's calling for an evaluation and comparison of public health impacts that shall include consideration of impacts that may result from single, intermittent, or frequent use of or contact with the chemical, including dermal, oral, and inhalation exposures. Factors to be considered include, but are not limited to, acute or chronic toxicity, bioaccumulation in humans, carcinogenicity, cardiovascular toxicity, dermatotoxicity or toxicity of the skin, developmental toxicity, effects of electromagnetic radiation that includes ionizing radiation and non-ionizing radiation, endocrine toxicity. This is a very significant toxicity to us in this course. Epigenetic toxicity, which is related to endocrine toxicity. Genotoxicity. Hematotoxicity or toxicity of the blood. Hepatotoxicity or toxicity of the liver. Immunotoxicity. Musculoskeletal toxicity. Nephrotoxicity and other toxicity to the urinary system. Nephrotoxicity is toxicity to the kidneys. Neurotoxicity. Ocular toxicity or toxicity to the eyes. Organ or tissue system toxicity. Ototoxicity or toxicity to the ears. Persistence. Reactivity in biological systems. Reproductive toxicity. Respiratory effects. Toxicokinetics. Any hazard traits not listed above that relate to adverse impacts on human health, and adverse impacts on sensitive subpopulations. Often there are significant overlaps among these toxicities. A chemical, by eliciting a toxic response in one area, is also producing toxic responses in another area, or may be producing multiple toxic responses in multiple areas. Because of the focus of this course on sustainability, anything that impacts future generations is particularly significant, and therefore let me call your attention to developmental toxicity, endocrine toxicity, and epigenetic toxicity, which overlap considerably, since these forms of chemical adverse effects are strongly related to the developmental welfare of future generations, which represent a vulnerable subpopulation. This is Dr. Theo Colborn. Dr. Colborn is one of the leading lights of endocrine disruption research and education. A number of years ago, Dr. Colborn produced this picture of a baby with the words beside it, experimental subject. The picture beautifully captures our concerns about the adverse effects of endocrine disruptors. Dr. Colborn is a co-author with John Peterson Myers and Diane Dumanovsky of the landmark book in endocrine disruption, Our Stolen Future. We will encounter this book later in the course. The definition of an endocrine disruptor. An endocrine disruptor, or ED, is an exogenous substance or mixture that alters function or functions of the endocrine system and consequently causes adverse health effects in an intact organism or its progeny or subpopulations. We've seen this already. Now, endocrine hormones normally function at extremely low concentrations. A large body of scientific evidence indicates that endocrine disruptors can disrupt normal development, sometimes at environmentally relevant concentrations to which people are being exposed, to produce impaired organisms. The best place to find the scientific literature for endocrine disruptors, including with interpretations for lay people of key papers, is at the site developed by John Peterson Myers, OurStolenFuture.com. Understanding how to avoid endocrine disruptors is thus of vital importance as green chemists seek to develop chemical products and processes that do not compromise the health and welfare of future generations. Finally, in seeking safer consumer products, the California Department of Toxic Substances Control is focused not just on the human dimension. The department seeks also to develop safer alternatives that are devoid of adverse ecological impacts. In pursuing this direction, factors to be considered include, but are not limited to, acute or chronic toxicity in aquatic, avian, or terrestrial organisms, adverse impacts on aquatic ecosystems, including but not limited to aquatic sediments, adverse impacts on terrestrial ecosystems, adverse impacts on environmentally sensitive habitats, including but not limited to habitat loss or deterioration, adverse impacts on habitats essential to the continued existence of an endangered or threatened species, and other factors affecting the ability of an endangered or threatened species to survive or reproduce, adverse impacts associated with population loss, decline in population diversity, or changes in historical communities, and adverse impacts that can cause vegetation contamination or damage, including phytotoxicity. A large number of commercial chemicals produce adverse effects on human health and on the environment in these various factor areas that we have been considering. In the next lesson, Professor Bruce Blumberg from the University of California, Irvine will become your lecturer and will go on to consider the obesogen hypothesis. The idea that through endocrine disruption effects, synthetic chemicals may be partially responsible for the obesity epidemic that we are seeing in the United States and throughout the world.